Welcome to the second talk in this slot. It's going to be Kalen Pennington, Immutable Programming, Writing Functional Python Code. Please give him a hand.
Morning. So, good morning. Wait, we're also missing this projector. It would be a bad time. Like, lots of code. It's hard to talk through code without the code. Let me double check that it's not on my end. Oh. Extend to the right. There we go. Okay. Sorry about that. Right. So, who am I? I'm Kale Pennington. Yes, like the vegetable, but with a C. I work for edX, which is it's the leading open source nonprofit education provider. So we were founded by MIT and Harvard, and we have universities that publish courses on our site from all over the world. And really, so if there is a thing you're looking to learn, you can go to edX.org and find a class there. And so why am I here? Well, edX is a Django shop, so I do Python by day. But at night, I also write Haskell for fun, not really for profit yet. And there's patterns that I've picked up in Haskell that I think are really pretty useful for writing Python as well. Now, the biggest difference between Python and Haskell, in my mind, is that Haskell is immutable by default, and Python is not. And that difference, well, so what the immutability that Haskell has and really forces on you means that it's much easier to think locally about what you're working with and not have to worry about its effects on other parts of the code. And so I think using immutability in Python really can give you that same advantage. And I guess a way to think about that. So if someone gives you a value in Python, right? You have a nice box, and it's Python, so the box is clear. You can look in at the insides, right? There's not Java style, strict privacy rules. And there's probably some levers and some knobs on the box that you can use to make it do the right thing, do what you're looking at. The problem is that box probably also has strings attached, right? There are going to be things there are going to be references to that object, or maybe to internals of that object, and you don't know where those strings go. On the other hand, if someone hands you an immutable value, it's basically a brick. It's just going to sit there. It might have some numbers painted on it or whatever, but it's just solid. There's nothing can change. And what that means is you can build on top of it safely. So I guess to start, what things in Python can you see that are not maybe signs of mutability? Really, if you're assigning to an object's attributes, if you're modifying if you're modifying items in a dictionary, calling a method that modifies the object, like adding an item to a set, or even if an object is changing itself internally. Those are all really sort of signs of immutability and things that might bite you later. Immutability in Python, you can assign new names to things. That's certainly very useful. You can read attributes off of objects. You can read methods that are read-only. Most things in Python are mutable. Most things you can change. Lists, dicts, sets, objects, really any of the sort of things that you're building up, that you build up to rather. And it's really the primitives are the immutable values. Strings, numbers. Frozen set is a new one, it's useful. Tuples, nested tuples. If you have an object inside a tuple, you're back in sort of a mutability zone. But there are some other tools too. So properties. Properties really give you the ability to create. They give you additional computation on immutable objects, and we'll see some examples. Tuples, and I'll talk about named tuples. All of those things give you immutability and kind of tools for being able to think locally about code rather than worrying about kind of having to worry about the broader context. And then I'm also actually going to talk about the sort of the command pattern, which lets you separate things that are inherently immutable, like the world, user input, things like that, from the core of your application, which you can make less mutable. And so I'm gonna do this talk using the engine of a game of tic-tac-toe. It's admittedly very simple, but I think that's sort of that's kind of the plus. You probably would have written something very much like this if I'd asked you to write tic-tac-toe. And it's got lots of mutability built right in, right? We're going to modify the board by assigning to elements of a dictionary of a list. Taking an action on the board will change it. And that's really that's sort of that's the setup. This code actually already is using one of the sort of tools I mentioned. It's using a property to compute the current player, because the player is really just a function of what moves have already been played on the board. If no moves have been played, we can say it's player X's turn, and otherwise we can say it's O if player X has made more moves than player O has. And that means that we don't have to worry about when, at the point where we change the state of the board in do move down there, we don't have to worry about also modifying self.player. And that just, again, it keeps the number of things you have to think about when you're writing code a little bit smaller. We can write some tests. Unfortunately, the tests fail as written. Some of you may have already seen the bug. That's okay. I'm going to run through okay, we got this bug. How do we get past it? So let's write a bigger test. We're going to store the state of the board so that we know what it is before we make the move. We'll do our move, and then we'll store it again afterwards. And we can compare them. They're sets. We can subtract them and see what values are different between before and after. And when we run that test, what we find is that after you make the first move, you actually have an X in the entire first column of the game board. That is clearly not what we were trying to do. So what's going on? Well, the problem is in the setup. The list, the internal list. So we're taking a list of a single no player assigned. We're making 3 copies of that list, and then we're making. Well, it turns out we're actually making 3 references to the internal list. Code like this will work. That will give us the correct results, because we're actually making 3 new lists to get you the 3 rows in the board. But I'll be honest. I knew the first line was a bug because I wrote it while I was writing the code for the talk, and had all of this failure happen live to me. It's not obvious. I often see, this is spooky action at a distance, right? We made one change to one row, and actually made changes to all 3 rows, and it makes me sad. So, what can we do about that? What's the sort of the way forward? I mean, we can write the safe code, but we have to think about writing the safe code every time we run into something like this. If we use tuples instead of lists so that they're immutable rather than being mutable like lists are, we actually have the same 3 references to the same object. But it doesn't matter, because that object can't change. So we can't modify the object. There can be no spooky action. And we can see that, so that's sort of the setup. That's maybe a fix. We can actually go further. We can make the whole board state immutable, and we can see that cleans up the tests a lot too, right? If we have a board state that we initialize, and then making a new move just gives us a new board state back and doesn't modify the original, then we can compare them. That would be the sort of the modified code, where we're going to create a new board state every time. I mentioned before that named tuple was going to be something I'd talk about, and this is actually one of my favorite ways of using named tuple, because it gives you all of the kind of benefits of a class more or less for free. But let me talk a little bit about what named tuple actually is first, just for anyone who hasn't seen it before. So named tuple, it's in the standard library in the collections package, and you can just use it to create a new tuple class. You're creating a new class with it when you call this function, and that class takes arguments, whichever arguments you specify as the second parameter to the named tuple call, and those attributes you can access by name. And it's derived from tuple, which means that it is immutable. And you get all of the nice class things for free. You get dunder equals. You get you can hash it. You know, it's sort of a nicely behaved small object. It doesn't give you default arguments, so that's what this line is doing. It just injects default arguments into the class. It's a little bit. I wish there were a cleaner interface for it, but it is what it is. So what is making the board state immutable do for the move action? It makes it a little more complicated, right? We need a helper function that is really just it's sort of the tuple equivalent of assigning to a value in a list by just taking the start of the tuple and the end of the tuple and injecting your new value in the middle. And then we can use that to swap in a new entry in the new row, and then swap the new row into the new board, and construct a new board state to return. Now, if someone has already played that move, we can actually just return the current board, and we could return a new board that's a copy, but because it's immutable, we don't have to worry. We can just return a new board with all the same, return the same board, and the caller can essentially be none the wiser. Now, I mentioned commands before. So this is the state of the main function after we've converted to an immutable board, but it's got a lot of sort of a mix of things in here, right? A bunch of things are happening all at the same time. We have input, we're parsing the input, and then we're modifying a set of states. This lets us do things like undo and replay and things like that. But we can actually separate that out. So this is the command pattern. So we can pull the input gathering parts into a function that takes a board state and just gives you back what does the user want to have happen to that board. They want to undo something. They want to switch back to an old state, or they want to make a new move. Those objects, again, we'll make them named tuples or subclasses because they don't need to change. They don't need to be mutable, so we may as well make them immutable by default. And each of them can have the same interface to modify the state of the boards or the history of the boards, and they can all just return. That, by separating those out into a standard set of classes, we clean up. Well, we can test them, right? So now we don't have to validate user input. We don't have to mock user input or anything else. We can just validate that the commands work. And it cleans up our main game loop. It's a lot shorter. And And it's very consistent between, we get a new action from the player, we apply that action, and we repeat. You'll notice up here we actually have two different types of players. So that's another advantage of using something like the command pattern, is we can write a random bot that just returns a random move every time. So the last, I guess, thing I want to talk about is around, so say you wanted to iterate over all of the board states in tic-tac-toe. Now, admittedly, again, tic-tac-toe is simple. Maybe this isn't a super interesting problem, but I think the iterate over a lot of states of things while you're searching or while you have a lot of data that you're processing, that's a pretty common pattern. We can do it in the mutable version, right? So this is back to our old mutable version of code. And we can see we can make a move, we can yield the board. Well, in fact, we're going to yield the board, and then we're going to yield all successors of the board. And then we can roll back the move afterwards, right? Because we have to reset so that we can make the next move in our set of candidates. But this code makes me sad. The spooky action at a distance jumps up again. If the caller of this method, who's doing work on the boards that we're yielding, if they make a move, that will break the iteration, right? We'll lose an entire swath of the search space because that move has already been made. Okay, great. We're smart. We can fix that. We'll store the whole board state, right? Before we yield, or before we make any moves, we'll store the whole board state, and then we'll revert after we yield the rest of the iteration. It's better, right? It means the caller we make sure the iteration happens correctly. But it makes the caller sad, because with this, what happens if say I want to find the 5 most interesting tic-tac-toe boards. So I iterate over all the tic-tac-toe boards, and I store them. I find the most interesting 5, however you define interesting on tic-tac-toe. At the end of this, I'm going to have 5 pointers to the same board that is at the state of the last point of the iteration. Because again, this is mutating the same board over and over. So that's not great either. If we move to an immutable case where what we're yielding is states of the board, we don't run into either of those problems. And frankly, we're not doing much more work than we were here, because here we're having to copy we're having to copy the board every time just to keep from being messed up by everything else. Now we can go further, actually, and we can give the user some input into how to do this search. So say we wanted to end the search after the board is after the game is won, right? This search function will it'll fill up the board in every way it can. We can write a filter function that is going to take the states that we're about to iterate over and tell us what order to iterate them, or what we want to do, what we should do next. But again, it can't. We're sort of providing a very narrow window for the user to affect the iteration in an expected way, so we don't have to worry about this, the problems. This is the sort of the filter function I was mentioning before. We can just check if the current board state is a winner, and if it is, we won't iterate anymore. And we can go through that, actually run that code, and my laptop will chug away for 30 seconds or whatever it is and get some stats about tic-tac-toe. So I guess what is the thing I want you to take away from all this? Using immutability in your code can help you concentrate, make it so that you can focus on the code you're writing right now, and not what is someone going to do that might mess my code up, or what am I going to be doing that is going to mess someone else's code up? Like or some other thread's code up. Like it lets you just focus on the code you're writing right now. And you can use these properties, tuples and name tuples, the command pattern. All of those tools really get you those are sort of the key tools in my mind for getting that local thinking in your code. And I guess I'm it. I'm a few minutes early, so we have lots of times for questions.
If you have questions, just come up to the microphones, please.
Mike.
I have a question.
Hi.
So in your code there, when you wanted to splice in a new value in the middle of a tuple there, you had to write a little helper.
Yeah.
And that kind of sucks. And
Yes.
so in a lot of other languages, like purely functional languages, you use maybe a lens or something like that. What approaches do you have for that?
I sort of took the helper method because it was the easiest. I don't know where that code is. It was the simplest thing. Like as I was just writing the talk, I could see. I mean, I think you could take, so for tuples, for instance, I could imagine, and I'm not sure if I think you can return a value from setting a dict, or setting an item in a list. Not 100% sure, but so you might be able to use set item to essentially make this helper a little bit more intuitive. Not sure about that. I don't know, I hadn't thought through like how would I clean up this, especially in light of things like lenses you would use in another language.
Hey, you made it through without using the M word. In terms of immutable data structures, is there a specific kind of immutable data structure that you'd like to see in the core language, and why?
I think as far as the sort of bigger structures like lists and maps, I think those would be useful. I don't know if they need to be in the core language. I mean, I know there are several libraries out there for doing that have sort of all of the immutable data structures, all of the standard data structures, but written as in an immutable fashion. I think if you take I guess I don't actually think that you would want to take Python and turn it into Haskell, right? Haskell exists and is useful. I think having the tools available in Python so that you can use immutability when you want and when it makes sense is, I think, the core thing for me. And so that, from that perspective, I'm not sure immutability of, say, lists and maps are huge. I guess an immutable dictionary would be probably the biggest thing, because that doesn't exist.
So you're also on Team Frozen Dict?
Sorry?
Team Frozen Dict. We want Frozen Dict as well as Frozen Set, right?
Yes. Yes, I think Frozen Dict would be helpful.
Hi, good talk, interesting talk. Have you, in your work in this topic, how do you deal with, like we have this huge library ecosystem for Python, and as much as like you say, Python's Python, it is what it is. It's not Haskell, it's not Erlang, and so it doesn't have all those nice little mechanisms in there to help validate the immutability of our data structure.
Yep.
But oftentimes when we're dealing with other libraries, like that's not necessarily something that they were pursuing or that they care about. And
right.
So, that's one of the things that I struggle with sometimes with Python is that you get this miasma of references that you have no way of keeping track of. Is that something that you've, given some thought to, or how do you approach that sort of problem?
I think for me, mostly I will sort of make an effort to use immutable things when they make sense and are useful in the code I'm writing. I guess an upside is most Python doesn't expect to be able to modify, like, if you're passing an object into a library, it's, unless it needs to do mutation on the object, like most libraries aren't setting random values on your things. But yeah, I mean, as far as dealing with all of the mutability coming at you, I think it's more of a question of making a practice out of not mutating things, and sort of, if you can just use something like the command pattern or otherwise kind of have the immutable core of your application that things come into and go out of, then you can at least kind of maintain that.
Gotcha. So it's kind of keeping the code that you're focused on packaged separately from, like, for instance, the calls to your external libraries and whatnot.
Yeah.
So you at least have control over the mutability of the structures that are coming into and out of your code.
I mean, I think that's, given sort of where Python is and the fantastic libraries that we have and that you want to be able to use, that's kind of what, I think that's all you really can do at this point.
Cool. Thank you.
Are there any performance issues around the fact that, let's say, if in Haskell or other functional languages that emphasize immutability, presumably the language is designed in a way that you don't spend too much time making kind of like almost identical copy of something else, while in Python there is no particular consideration, or it actually works out fine and it's not an issue. So what I'm saying is, like, if you make a copy, it looks like you're almost making the copy of this huge board and you just like change one cell and you do it like over in a loop. Wouldn't that, I mean, I haven't thought about it carefully, but wouldn't that cause a problem unless you have some special language support, or it's not really a big deal?
So yeah, I didn't really get into a lot of the like immutable data structure type stuff in here, but typically what happens when you're using an immutable data structure is that you might replace like the top level tuple, but it's going to have references to all of the old. So imagine a 1,000 by 1,000 board instead of a 3 by 3, right? If you need to change one square in that, you'll replace the 1,000 length tuple at the top, at the sort of the spine of the structure, and you'll replace 1,000 length tuple at the row. But you're going to have the same, all other 999 tuples, you're not going to touch. And they're going to stay. So you're really only making essentially two new tuples every time you modify that board. And that's sort of the typical pattern with immutable data structures, is that they will have that notion of, they're often based on trees, and you can sort of swap out a small sub-portion of it, modifying kind of the spine of the data structure without having to create a new copy of everything. And that can actually be a plus. If you went back to the iteration where we had to save a copy of the board every time, you can imagine if that were a 1,000 by 1,000 board, actually doing the copy of that so that we could roll it back again would get expensive in the mutable case, and is perhaps less expensive in the immutable case where you can just swap out the handful of the row and the column.
But it doesn't work as is. The way you described is how it could be done, but that's not what happens as of right now, or it already that's not what happened in your code, right?
That's what happens the code as written, that replace function.
Oh, okay, so it's already, I see.
Yeah, I mean, the replace function is doing a little bit of probably extra work, because it creates, it like slices the tuple over here and it slices the tuple over here, and so you're creating probably 3 or 4 tuples every time you call replace, but it's still using references to all the other things in the original tuple.
Thank you.
Yeah.
I think you've touched on this a little bit, but I'm curious, to what extent does this strategy work if you don't have immutable data structures at your disposal?
I mean, I think so. Yeah, you're definitely, if you're stuck with a mutable object, you mostly can't do anything except try not to mutate it if you don't need to, right? Or try and isolate the places in which you mutate it so that you have better control over it. On the other hand, there are, so like I think I mentioned earlier, there is, and not that I have used it, so there's, caveat emptor, but there is a library for Python implementations of immutable versions of data structures. I was just told that actually Joe, the previous speaker, wrote a C implementation of name tuple. So there's that, that if you want to, again, sort of worry about performance stuff on that end. But I think you just kind of have to manage the existing mutability is the unfortunate answer, I think. Is you kind of just have to work around it and do what you can to not use it.
So unfortunately, we're out of time. If you have further questions, talk to the speaker directly and give him a hand again.